fine. If you want to just tune out, that's fine. Either way, I'm just going to give the lecture to Missoula for the next 15 minutes, and then we'll just repeat it here in the classroom. So we're all, like I said, two for one deal today. All right, so Mark, hopefully you can hear me just fine. Like I said, if you can't, give me a call back on my phone. We'll see what we can do on this end. But I'm sitting here in Browning. I have 15 or so students. A lot of them are in the building trades, non-traditional students. I also have a lot of students who are in high school enrolled in the dual credit. So just a second ago, I went over the banking problem, and I think the consensus at the end was go green. We're going to have to use renewable energy whether we like it or not. But today, what I wanted to show was a comparison on human energy and human power versus technological energy and technological power. So, and I wish I'd brought my fancy little pad with me. I didn't bring it. So what I'm going to do is just pull up an old lecture that I've used in the past, and I'll just use my mouse to kind of scroll around and just show you things as we go. So what I first want to do is just get an idea of how much energy each person uses per day. And unfortunately, the guys here in Browning can't see that well, but I'll show them here in a second. Hopefully everyone in Missoula can see just fine. So if you look on the back of your cereal box in the morning, or any any packaged food, what you'll probably see is a USDA calorie allotment. Anyone, you guys remember what that is? About what the United States Department of Agriculture says? What's it say there? Well, you can read it. Eyes are getting bad. Mold.
Contents.
It's got the contents, the sugars, the proteins, the fats, but it also should say how many calories.
Oh yeah, 160.
160 out of. It should be like 2,500 there. If you look further down, yeah, at the very bottom it says percent daily values are based on a 2,000 calorie diet. So you probably heard that before. Now, so what I've done here on the screen is just written out 2,500 calories. There's a range there. There's an average, and so what I've done is taken calories, so big C for calories, which is how many are on the soda bottle, and changed that into little c for little calories. And there are 1,000 little calories in one big calorie. Sorry, oh, no. There's a little noisy in the hall, so I closed the door.
Yeah.
So 2,500 big calories or kilocalories is the same as 2.5 million little calories. So that's how we measure metabolic energy. What's another example of how you might measure energy, like some units?
Watts.
Watts, we'll get to in a second. That's power. Another one would be maybe kilowatt hours. If you read your electricity bill, you usually say you use this many kilowatt hours. So kilowatt hours is another unit of energy. So we got calories, we got kilowatt hours. The international standard is joules, named after a British engineer named James Joule, who back in the day actually showed that heat and motion were kind of the same thing. So joules is what we use, and all I've done here, and I'll show you guys here in a second on the board, I've taken 2,500 kilocalories, multiplied that by 4,184, and come up with about 10 megajoules, or 10 million joules. So if we ever change energy units, you might say, oh, I need to eat 10 megajoules of energy per day. And of course, that energy is coming from fat, protein, carbohydrates, etc. So 10 megajoules is what each, might as well write that up here. 10 megajoules is what each person uses each day. You know what? I can't hear me. Okay, so somebody just mentioned that watts might be a unit of energy, actually a unit of power. And that's something that I really tried to emphasize really early on in my NRG 101 class, is that energy is one thing and power is a different thing. Energy and power are as different as speed and time, or speed and distance. So for example, you might be going 60 miles an hour in your car. That's a little bit like power. But if you go 60 miles, that's more like energy. The distance is kind of how far you went, or it could be, another example could be how much energy is in your gas tank, and then the power is how quick that gasoline's flowing out. So that's the difference between energy and power. So what I did here is I divided that 10 megajoules, 10 million joules, or 2,500 calories, by the number of seconds in one day, and I came up with about 121 watts. So each person, each one of us, is running at about 121 watts. Anybody watch the Super Bowl last night? Maybe? Okay. Most of those football players are running at much greater rate than 121 watts. That's why they're professional athletes. When you're asleep at night, you're running at more like 60 watts. Depends how much you're thinking, how hard you're working, etc. But each person has a metabolic power of about 121 watts. How does that compare to a horsepower? More or less? Maybe for some people. Most people are less powerful than the horse. Horsepower ends up being about 750 watts. So you can think of a human power as being about a fifth or a sixth of a horsepower, right? If you wanted to go play tug of war with a horse, it's going to take 5 or 6 of us to fight that horse. We're smaller, less powerful.
This one vehicles like say 400 horsepower.
Yeah.
750.
Yeah, that's a good point. So let's say you got a 400 horsepower car. That's, well, you'd have to multiply by 5, so it's a 2,000 person power car, about, right? So, imagine 2,000 people pulling the car down. Most cars aren't going that hard. I mean, normally you're too long in your truck, you're doing 20, 30 miles an hour, you're only running at 20, 30 horsepower. You're not running full out. So that's how to think about power, difference between power and energy. Okay, so that's one human power. Now what I want to do is compare human metabolic power, caloric power, how much we compare that to technological power. So what actually goes through our machines. And so that's the next slide here. Now, just a second ago, we did the banking problem. I threw the number 3 billion on the board. I threw the number 50 million up on the board. This next one's a little tougher, and I'll write on the board again. But it's 500 exajoules. So I already told you what a megajoule was. It's 10 million joules. An exajoule, now I'm forgetting. It's an exa is 10 to the 18th. So kilo is 1,000, mega is 1,000,000, gig is 1,000,000,000, tera is 1,000,000,000,000, peta is 1,000,000,000,000, and then exa. 500 exajoules is how much energy all the humans on the planet use every year in their machines. So add up all the jet fuel that goes through all the jets, add up all the coal that goes through all the coal-fired power plants, add up all the gas that comes out of the ground. All of that energy is 500 exajoules. And we'll do a little math on the board here in a second. And Mark, you can probably do a little more on your end. But what I've written is 500 times 10 to the 18th, big number. And I've divided that by 365 days. And then I've divided that by 7 billion people. And I come up with about 200 megajoules. So that was kind of a long calculation. But if you remember, that 2,500 calorie drink had 10 megajoules in it. And I just told you that all of our planes, trains, automobiles, television sets, iPhones, what have you, consume 20 times that, 200 megajoules per day. So what's that mean? Well, it means that each one of us essentially has 20 people working for us. You know, if you wanted to drive your car, you'd have to have, you know, your entourage of folks running behind you. So fortunately, we are at a place in technology where we no longer have slave labor, right? You look at the Egyptian pyramids, you look at what happened in the colonial South. We now have machines do our work for us. But we're doing that at a rate 20 times the rate at which we could do it on our own. So that's what we are right now, the average person on planet Earth. Now, North America was at 200 megajoules per person in 1956. It's 50 years ago. North America now is at 1,200 megajoules per day. At 200, it's just the average person. There's I think the statistics, I mean, there are about 1 billion people in the world still that don't use any electricity at all. They don't have it. They don't have the access to it. So I guess what I'm showing here is, again, I showed the banking problem. We're now on a trajectory where we just keep using more and more energy, but I've shown you that there's really not much left for the Earth to give, and that's another argument for using sustainable energy. So do you see the example between human energy and technological energy? That was the main point of that. So, all right, I'm going to stop the lecture. Sometimes the software doesn't work all that great. That was 11 minutes. I said it'd be 15, but there you go. Missoula, I hope you can hear me just fine. I'm going to wrap it up here in Browning, and see you guys on Wednesday.